Well, good morning, all you ME3311 folks, fine folks. Um, Going to pick it up on binary isomorphous phase diagrams. This will be part two, and the other one got cut off because I didn't realize I could do a full 50-minute video or whatever it was. But at any rate, this will be much shorter because I was told to keep it to 15 minutes or so. So I want to go over the things that were lost in the last section. And I was just starting to talk about, we were doing a copper nickel binary phase diagram. And we had gotten to the point where we had gotten the compositions of this at 1250 and 40%. We got the liquidus composition of 32% nickel. This would be liquid, and this would be solid down here, of course. And so we got that, the two compositions of the liquid being 32% and the solid being 45% by drawing our tie line. And then we wanted to find out the relative amounts. How much at this point right there, how much liquid is present there, and how much solid is present there. Because again, this is a two-phase liquid plus solid, kind of a slush, you might call it. But at any rate, we went to the lever rule and we did that, and we came up that it was 38% liquid, and again, due to the conservation of mass, it was 62%. Then it would be 62% solid. So, but at the end of the day, so to speak, we still have to come up with, at this point, just 40% nickel. So what changes here is that the relative amounts are going to change. And so what we need to do is just take the percent of how much liquid is there and multiply times the percent that nickel is in that amount, and then take the solid amount, the 62%, and how much nickel is in the solid, and multiply those two together. So when we do that, the actual amount of liquid, the liquid has 12% nickel, and the solid has 28% nickel at that point. So that's how we get the ultimate 40% or baseline composition of nickel that we start off with at 1250 degrees. Okay, so that's how that works. Now, I'll point out one thing here. I got two green composition numbers here, and just to show how this works, if we had the same 1250 isothermal tie line here, but we had 35% instead of 40, well, the compositions for the liquid and the solid would be the same. It'd still be 32% for the liquid and 45% for the solid. And then if we moved over to 43%, again, same thing. 32% is the liquid nickel content, and the solid would have 45% nickel content. Even though these overall have changed, what ultimately, why they have the same is because what ultimately separates them would be how much liquid is present here as opposed to how much liquid is present there. So the vernier scale here is basically the relative amounts that are changing from liquid to solid, even though the compositions are remain the same. Okay, so to summarize all this, kind of, the three questions we'd be asking ourselves when we get into a two-phase region like that would be, first of all, what phases are present? Second of all, what are the compositions? And third, what are the relative amounts or weight fractions of those phases present? So just to summarize it here, tie line gives you the composition of that phase, and it defines the end members and the solubility limits, okay, where it intersects that liquidus line, where it intersects the solidus line. Those are the end members and or the solubility limits. Whereas the lever rule gives you the relative amounts, how much liquid is present, how much solid is present, and by doing that, it captures the notion of phase separation between liquid and solid, and also, of course, conservation of mass. So those are the key items, that concepts and terms that when we get through here. And now I want to go into show you a little bit about what the phase transformations look like. If we go through, let's say 4 or 5 points, what they might look like. So let me draw this up again. I'm going to do just an abbreviated close-up of another copper nickel, I guess. Only this time we're going to have a line, a straight vertical line coming down at a certain composition, and let's call this 35% nickel. And we're gonna look at another color here. We're gonna look at, let's see, 1, 2, 3, 4, 5 different points. So we're gonna have one here. We're gonna have one just inside, one in the middle, one almost out, and then one completely out. So we'll call this A, B, C, D, and E. Okay, so what we want to do is we want to look at microstructures. Now, we define microstructures early on, and it's just the structural features of an alloy that are subject, obviously, to observation under a metallurgical microscope. So what I'm going to do then is I'm going to take and I'm going to draw what you would see, and I'll try to draw this like so. 1, 2, 3, 4, 5. Okay, so this will be at A, B, C, D, and E. So what we're going to do is we're just going to kind of look at that and see what's taking place. So at A, it's obviously all liquid. This is all liquid, and this is all solid. And of course, this is going to be liquid plus solid in there. And so it's going to be all liquid. And its composition is clearly 35% nickel. 35% nickel. All right. Now, here, when we just go through, the temperature drops, and now we're into this two-phase region, and we go below the liquidus line. So now we begin to have just a little bit of solid starting to form, starting to show up in the mix. Okay, just a few little grains of solid, but the rest of this is liquid, and these little solids we're going to call just alpha, because that's what we call a solid phase of a metal, is alpha. And so we're going to have alpha, so we would need to then look at drawing a tie line for each one of these. And so the tie line for here, since it's just inside, we're going to go ahead and use that point and draw a tie line, that whatever that temperature is, because these all are represented by specific temperatures. But that really doesn't matter what they are, just where they're placed. So at any rate, so when we draw this, we know that the liquid specifically is still going to be at 35%. So the liquid will be at 35%. Let's do it this way. Liquid at 35% nickel. Okay. And the solid, or the alpha, okay, the alpha is going to be at, well, we have to draw this tie line, and so wherever it intersects here, we're going to have to come up with some kind of willy-nilly composition, and just for let's just call that 46%. So this will be 46% nickel. So the alpha solid is at 46% nickel, and the liquid is still 35% nickel. Okay, so now let's go down here to C. So C, of course, we're dropping the temperature, and so all of these alpha particles begin to, enlarge. All right, so we still have these as alpha particles, and we still have some liquid in here. So again, we need to construct a tie line at that temperature all the way across. And again, we define the two end members just like we did up here. And come to find out that the liquid here, when we look at this and drop this down, arbitrarily pick a percent, this is going to be at 32%. All right, so this will be at, let's just call this 32%. Okay, so liquid would be at 32% nickel. And the solid, when we draw this all the way across and where it hits the solidus line, let's just come up, and we know it's going to be less than 46, so let's just call this 43%. So the alpha solid will be at 43% nickel. 43% nickel. Okay. All right, and then finally down here at D, we're very close to being almost out of this two-phase region. All right, and so we know there's going to be all of these alpha particles will have been enlarged. So because they're almost about ready to turn completely solid, so they'll look like that, and so these again will remain all alpha, and we have a little bit of liquid left in here. Okay, so again, drawing a tie line with this being so close to that solidus line, we'll just use that as the basis for it, and then have this as our two end members. And so the alpha, the alpha here is right on the solidus line, which is at 35% nickel. So this will be, the alpha be at 35% nickel. All right, and then whatever liquid here, go back this way, and just again be something less than 32, so we're going to call it 24% nickel right here. This would be 24% nickel, so the liquid then would be at 24% nickel. All right. Okay, and then finally, when we get to the very bottom, of course, all we're going to have is just all of these giant multiple alpha grains. And of course, no liquid present, and so it's just going to be at 35% nickel. All right, so this is just a representation of these phase transformations and what they look like. Now, of course, we could have gone back and used the lever rule on every one of these and determine, how much liquid is present, how much solid is present in these three indications here at B, C, and D. And so that would just be utilizing the the lever rule. Okay, now what I need to introduce you to right now is we're going to jump into another type of phase diagram, and this is going to be what we referred to earlier as a type 2 diagram, where there's going to be partial solubility. Okay, this was all complete solubility. This diagram is going to be partial solubility. So let me draw this one, and it's a little more challenging, a little more abstract perhaps, but let's see if I can get something that looks halfway decent here. And I'm going to start with a line, a straight line looking like this, and then I'm going to go up here to a point, down here to a point, again up here to a point, and then down here to a point. Now I'm going to pick a point somewhere like there and draw this. Okay, so that's not a bad representation. But again, this is going to be a binary, and again, this is going to be called a eutectic, binary eutectic. All right. except it would be nice if I could spell it right. Eutectic. All right. So a binary eutectic diagram is what this is going to be. Phase diagram. Okay. Now, we're going to have, again, components A and B. And this is going to represent the melting temperature for A. This is going to represent the melting temperature for B. Okay. Now, notice that one's obviously lower than the other. But so you imagine up here, this complete region would be all liquid, and down here would, of course, would be all solid. All right. And then we have, this would be the area over here known as the alpha. All right, and this over here would be another metal, perhaps beta, over on this side. Okay, now, and then, so if this is a single phase and this is a single phase, and in here we're going to have another two-phase region, just like we had before. This will be alpha plus liquid. This is going to be beta plus liquid. And then down here, this is going to be, obviously between here and here, we're just going to have alpha plus beta. All right. So, you know, that's how we have the single phase, three single phases, and three two-phase regions. So that all works out nicely. Now, this is a very unique point. This is referred to as the eutectic point, which represents the lowest melting point on the diagram. Lowest melting point on the diagram is the eutectic point. And then, of course, it would also have, if this is the eutectic point, we also have a eutectic composition, whatever it might be. Okay, so we have eutectic point, have eutectic composition, and at this eutectic point we'll also recognize being the eutectic temperature, or temperature eutectic, okay, whatever that might be. All right, now there's something unusual. Look at this. Notice as we have freezing point depressions here, and if you look at this, as the more we add a B, and there goes the timer, so I'm going to have to shut this down here, but the more we add B to this mix, this is 100% A, notice how the freezing point, or solidifying point, gets lower and lower and lower. Okay, even though this is a higher melting temperature than that. That's the bizarre side of this. Okay, you would suspect that the more you add of A to B, it would bring the temperature down because A melts less than temperature than B. But here is a very strange. You have freezing point depression here going, really, and in both directions. So that's unique. That's unique to these binary eutectic diagrams. And so when I start the next video, and I'm going to have to do a part 2 on this one, or part 3, I guess, and we'll go over what alpha is, we'll go over what beta is, and then we'll go over, you know, what this, essentially what this eutectic point is, which we've already done, okay? Because I'm running out of time and I don't want to mess this up. So we'll make another one, part 3, and we'll get that out to you as quickly as possible. So we'll see you then.